Hey trigonometry students, this is your lesson on section 3.4. We are going to be learning about something called linear and angular speed, and these are going to be more application problems. So let's go ahead and get started. All right, so this right here is linear speed. It says, suppose that a point P, like this right here, moves at a constant speed along a circle's radius. Okay, so it's moving at a constant speed around our center O. The measure of how fast the position of P is changing is the linear speed. And if we say V represents linear speed, then this is what we would have. Speed is equal to your distance over time, just like velocity, okay? Distance over time. Or you can say this right here. Since we are referring to the distance around a circle, we call that the arc length. We're going to say that is our S. The distance around the circle is S. And so V equals distance S over time. And this is our formula right here for linear speed. All right, and this is an explanation on angular speed. And it says this: as point P moves along the circle, ray OP rotates about the origin. The measure of how fast the angle POB is changing is the angular speed. So we are figuring how fast the angle changes. So we're going to say our angle theta is changing with time. So we call it omega, this Greek letter right here, is equal to the angle over t. Okay, and again, in this formula, like in the last section, theta is measure of angle in radians. So here's a list of our formulas. Angular speed, we only have one right here. Angular speed is equal to theta over time. And then we already showed you this one, that velocity or linear speed is equal to our arc length S, distance over time. And then this right here, we can replace S with its arc length formula, which S is equal to R times theta. So replace R times theta, and for S, you get this formula right here, that V is equal to R times theta over T. Now, the next formula is similar to this one here, because we have theta over T, which represents our angular speed. We are given a radius and our angular speed, we can figure out the linear speed. Okay, so that is 3 different formulas that we are going to be using for linear speed. All right, so here is our first example, and we're going to have 3 parts to this. First part is this right here. So suppose that P on a circle with radius 15 inches and ray OP is rotating with angular speed pi over 12 radians per second. So right off the bat, we are given this information. Angular speed is pi over 12 radians per second. I'll write that, radians per second. And we also know R is 15. It's not going to help us in this first part, but we'll get to it. And then for part A, it says find the angle generated by P in 10 seconds. So time equals 10 seconds. So with this information right here that we are given, we're going to find the angle. And that formula that's going to help us is this one here. Omega equals theta over time. And we have omega, and everything agrees with this time measurement. This is per second. Time is measured in seconds. So plug in. Omega is pi over 12. And then theta is what we're solving for. and 10 is our time that goes in for t. Solve for theta. Multiply both sides by the 10 and we get theta is equal to 5 pi over 6. And then that is going to be just in radians, because this is time, that's seconds. This is radians per second. Our seconds end up canceling, so we have this as our answer for part A. Okay, so let's go on to part B. All right, so part B goes along with part A. It says, find the distance traveled by P along the circle in 10 seconds. So we're going with the same amount of seconds around the circle that generated our angle that we found in A. So we're going to be using the fact that we know theta is equal to 5 pi over 6 radians. And also, from the previous slide, we know that radius here is 15 inches, I believe. Yes. All right, so if we want to find the distance traveled by P along the circle, that is going to be our arc length. We have theta in radians, we have r. Let's use S equals r times theta to figure that out. So S equals 15 times 5 pi over 6, and multiply these together, we get approximately, let's see, 39.3 inches. Okay, and that is our solution for this one. Now in part C, let's go to it. It says, find the linear speed of P in inches per second. So this is referring back to the previous two. So linear speed, remember we had several formulas listed. I'll go back to those if I can. Let's see. Okay, so here are some of our formulas that we have. We can actually use pretty much any one of these to help us in figuring out what the linear speed is. But this first one is usually my go-to, especially if we have the arc length and we have the time. Okay, and we do have both. So let's go back or go forward and to this problem that we have here. So finding the linear speed in inches per second. So velocity or linear speed is equal to our distance s, arc length, over time. And we can plug in, I'm going to plug in the exact form right here so we can get a more approximate, closer approximation to our answer that we're looking for. This reduces to, let's see, 25 pi over 2. Right, so that's what I'm going to use in for our arc length, is 25 pi over 2. And then t is still 10 seconds. Now let's reduce that. We get 25 pi over 10, which can be reduced further down to 5 pi over 4 inches per second is what it's measured in. Okay, so this is our, what we're looking for, our linear speed. Sometimes you will be asked to find linear speed, just approximate the value in the unit of measurement that it's given to you, but here I just gave the exact value. You can plug this into your calculator and then approximate it and say inches per second as your unit of measurement. I'm really big on these last two sections, so just fair warning, on writing your units of measurement down. So on your homework, please do that. And also on any test or quiz that you will have following this, you will need to put your units of measurement down correctly. Okay, so let's go on to the next problem. All right, this is the second example. It says a belt runs a pulley of radius 5 inches at 120 revolutions per minute. Part A asks us to find the angular speed of the pulley in radians per second. Okay, so remember, angular speed is the omega equals theta over t. All right, so before we can figure out this angular speed, we need theta. And this is going to help us in finding theta. Okay, so in 1 minute, this pulley makes 120 revolutions. So what this means is 120 revolutions per minute. We will have an angle of, so multiply it by 2 pi, because that's one full circle, that's one full revolution. Let's see, yeah. And this right here is in radians. Okay, so now we have multiply 120 by 2 pi, you get 240 pi radians, because this is per minute. Okay, so there we go. And that is actually our angular speed right there too. But let's see, we are asked to find in radians per second. So we have our measurement for radians per minute. That is the angular speed there. Radians, that's what the theta is measured in, per time, minute, is what we have so far. So just do the conversion here at this point. So omega is equal to 240 pi radians per minute, or let's put it in seconds. There are 60 seconds in 1 minute, so 1 minute over 60 seconds. So divide this amount, 240, by 60, and we have 4 pi, and now we have radians per second. And we are done with this one. So many times you will be able to find your angular speed just from this statement right here, that it turns 120 revolutions per minute, or how many ever revolutions per minute. But you got to remember your angular speed, many times they want you to change it to per second in your problems. So make sure you do that. All right, so on part B of this problem, we're going to be using a bit from part A. We're going to be using the fact that we found our angular speed to be 4 pi radians per second to help us in finding the linear speed of the belt in inches per second. So the linear speed of the belt will be the same as that of a point on the circumference. So a point on the circumference of the pulley, okay? So it's being turned many times, and it's creating a greater and greater distance, and so it's creating a velocity too, the linear speed. So on this one, we had a list of 3 different ways to find linear speed, but with the information that we have, linear speed, we have omega, we have angular speed, and one of our formulas was the radius times our angular speed. And we have radius and angular speed. So there we go. We can find our linear speed by saying 5, and that's in inches, times our 4 pi, and that's in radians per second. So our linear speed is going to be 20 pi inches per second. Pretty much the radians just go away whenever you multiply it to anything that is a distance, like inches, feet, or meters, or whatever your unit of measurement is. So this one takes precedence over the radians. And you don't have to list radian inches per second. Just list inches per second, like this did right here. So there is our velocity, or sorry, our linear speed. I'm going to call that velocity all the time because I'm used to my physics classes that I've taken in the past. But anyway, there it is. And if you want to go ahead and approximate the value, if I say approximate this linear speed, then plug into your calculator, you should get about 63 inches per second. And we are done with that one. All right, so our last example here is about the satellite orbiting the Earth. So I'm going to draw us a little picture here. Here's the Earth, and here is something orbiting the Earth. These circles are supposed to be concentric, but I tried. All right, so we know the radius of the Earth. We can get that. It's 6,400 kilometers. And then, okay, read this. A satellite traveling in a circular orbit approximately 1,800 kilometers above the surface of the Earth takes 2.5 hours to make an orbit. So the radius of the Earth, like I said, 6,400 kilometers, but the satellite that's orbiting the Earth is 1,800 kilometers. So to get this total distance from the center of the Earth to where the satellite is orbiting around the Earth, we got to add these together. So the total radius, total R, is going to be the 1,800 plus the 6,400, which is 8,200. And that's in kilometers. Sorry, I'm going to rewrite that. Okay. All right, so the next thing on here, other than finding the radius, remember we're finding linear speed for this thing, because it takes 2.5 hours to make one full orbit. Well, one orbit around the Earth is one full circle. So theta, one full circle, is 2 pi radians. Okay? And now let's get our arc length. We can go ahead and get our arc length from this information right here. So one full circle gives us S equals R times theta, so 2,800 times 2 pi. And let's see, that gives us 16,400 pi kilometers. So that's our arc length distance around that is actually our circumference around the whole orbit of that satellite. Now, since it takes 2.5 hours to complete an orbit, this is your linear speed. Let's look at V equals S, since we solved for S, over T. We have time that is 2.5 hours. Okay, so plug in S, this number here, over T, 2.5. This is hours, and this is kilometers. And just reduce that. So, let's say 6.5, is that right? Yeah, 60 pi. And this is in kilometers per hour. Or you can say this right here. It's approximately equal to, if we multiply that pi through, let's see, I'm going to calculate that with my calculator. Okay, so let's do this together. I'm going to multiply. All right. So there is the approximate number in kilometers per hour. I'm going to write that down. So 2068.8. So 20609. Let's write that down. 20609 kilometers per hour. Oops, hour. Now let's look at part B. Okay, so in this next one, part B, it says approximate the distance the satellite travels in 3.5 hours. Okay, I'm going to be using, again, this right here. Another way of rewriting this, because we're approximating the distance, is solve for S. So multiply both sides by D. In the previous exercise, we found the velocity, the exact velocity to be the 6,560. Let's see, let me write that down. V was 6560 pi kilometers per hour. And then now we're asked to find its approximate distance traveled in 3.5 hours. So that's going to go in for our time. That's a new time that we have. So S equals, plug in your velocity and 3.5. This is measured in kilometers per hour. This is measured in hours. So the hours, the time cancels out. We're left with kilometers. And so S equals, approximate that. Calculator. Let's see. So 6560 pi times 3.5 equals. And there you have it. That right there is our approximated distance. So 72130 or 72131. Oops. And it's in kilometers. And there we go. We are done with this section. I will be assigning you problems very similar to these, hopefully, and you will understand them all, but I will be there to help. I'll see you all in class. Goodbye, everybody.